Now that we have finished looking at the libraries, let's have some fun with the computer. Now this isn't in any particular order. As each day goes by, I will pick a different topic and we can try and implement it within the machine. Now what we're going to look at today is the sine function. We've seen that we can generate the sine of a value, and we did it for just one single value, but what I'm going to do is generate it for lots of values, and then we should hopefully be able to see the actual sine function, okay, so the sine curve. Now I actually started off doing this, and I realised that the method I was using for doing it generated something that we could call a systematic error. But I decided just to continue with it anyway, just to see how that error would manifest itself within the actual function. But we will see that nearer the end of the video. What we're going to do now is just look at the actual sine function and compare it to what it should look like. Okay, so this is the little bit of code here. I'm not going to go through and talk through the code. You can always pause it if you want and have a look. But in essence, what we have is the values are listed here at the bottom. So we're going to go from, and again it goes all the way along the end of the page. I'm not sure whether I've got the if I can actually go down onto the next line. I think the assembler might get a bit confused, so I just ran it over the entire length. So we go from 0 up to 6.28. okay, so it's actually 6.3 in steps of 0.1. So that's us going from 0 to 2 pi radians, which is equivalent from 0 to 360 degrees, and we're going in steps of 0.1. So this should give us a good indication of the sine function and how it looks. Now we're going to pass these values into the subroutine here for our sine, and then it's going to pop them back out into R3, and then we're going to save them into this location here called sine_x, and you can see we've got as much as 64 values, and that's as much as we need here. So I've already ran through this simulation. Now I will bring up the actual machine here. So I've ran through the simulation, and if I get into the contents, so this is the final contents of the machine after we have ran it. Okay, so these are the contents here. Now the first lot of contents we've got here are the actual input. So the input runs from this 0 here, and it runs all the way up to we get to the 0 here. Okay, so all of those are the input values, and then the output values start from here. So I've taken all of these output values, which of course they're all in our fixed point number system, and I've decided what I would do is just put all the information I have into an Excel spreadsheet. So let's have a look at the Excel spreadsheet now, and we'll see exactly what the information is we have. So let me first of all, well, in fact I can leave it just the way it is there for the moment. So you can see here that along this column here we've got the angle and radians, so it goes from 0, 0.1, and it goes all the way up in differences of 0.1 all the way up to 6.2. okay, now I've then just generated the sine of those values within Excel. Okay, so I just used the sine function within Excel, and these are the answers that I should be getting. Okay, so this should be our final output. Now what I've done is I've then taken that output and I've put it into the 8.8 fixed point number system. So you can see here these are the actual values we should expect to see whenever we actually run it on the machine and we get the output in our 8.8 hex. Okay, now I've then gone through and I've ran it. So this is the actual the next column here is what I've actually ran on the machine. So these are the actual values that I do get. And you can see that these should match up. So 0019, and you can see that that one's out by 1, that's out by 1, that's out by 1. And if you run all the way down, most of them are out by maybe, they're either exact or out by just maybe 1 or 2 values, which is really excellent. You know, that's really good. Now what I've done is I've taken these here, which are the output from the machine, and I've generated the actual decimal equivalents. So these are the decimal equivalents. So these here should match up with what we have here in this column, okay? And you can, what I've done is I've ran through and I've picked out the difference, okay? So I've just subtracted one away from the other, and you can see the differences are really quite small. Now I've gone ahead and I will bring this in a bit, so hopefully you can see this. I've gone ahead and I've generated the functions in a graph, okay? So there's not a lot to see here actually. So you can see that the red one here is the blue one. The blue one is the actual sine function, which is generated by Excel. And the red one here, and you can see it just underneath, there's a little bit peeping out through here, and there's a little bit peeping out through here. But the red one is what has been generated by our computer. So this is really quite accurate, and it's only off a little bit round about where we've got the value of 1 and the value of -1, but it's out by very small amounts. Now, it's not particularly scientific in terms of how I define the differences between these two. We're just kind of having a wee bit of fun, having a look at hand and eye, just to see what we're able to generate. So it looks like it's relatively close. I checked out the percentage error, and we're talking about mostly less than 1% percentage error for every value. Now that's not really surprising, because the reality of it is that we only work out or generate the sine function over just one of the quadrants. So we only generate it over this quadrant here. And then the next quadrant is just a copy of this quadrant, which has been flipped. And then the next quadrant is a copy of this quadrant here, which has been flipped on the x-axis. And the final quadrant has been flipped again. So we only need to generate it for actually from 0 to 90 degrees, and all the rest of them are just flips or changes to just a copy. Okay, so I'm quite pleased with the sine function. It looks it's worked out quite well, and we've got a good approximation. Now, as I mentioned earlier, when I first started off doing this, I actually did it slightly different. And by doing it slightly different, I introduced a systematic error. Now, what I mean by that is that instead of defining this DC here, I defined some other thing. I called it DC, and I called it X, and I went from F0.0, and then I put in a comma F0.1, and I put a comma F6.28. So rather than have all of the values here written individually, I generated this little thing here. Now, I took this here and I ran it into another subroutine. So the other subroutine I created, what it did was it took the first value here and it took the last value, and it just added 0.1 on continually. And it generated all of these points here. So it generated all of these for us, okay? But then whenever it generated all of these points, I actually did the addition in terms of adding the 0.1 on within our fixed point system. But the problem is that 0.1 in our fixed point system is not an exact value. And in fact, and rather than getting 0.1, you're going to get something like 0.0997 something or other. Okay, now that's no problem if you're only doing it for one value, but I generated this for all of these 64 values. So it means that whenever I generated the first one, it was out by 0.00, the next one would be out by 0.002, the next one would be out by 0.003, and if you do that 64 times, then as you work your way along, each of the values was going to be out by a little bit more each time. So this is what I mean by a systematic error. And this error occurs because we don't have an exact value for these decimal numbers within our 8.8 fixed point number system. In the same way, for the number 0.1 in a floating point number system, we don't have an exact value for that number. Okay, so there's always going to be errors. Plus, the issue we have as well is that we don't have any real kind of smart rounding mechanism, okay, that helps to get rid of these systematic errors. We do have it within the floating point unit, which will come in the next course, but this is just a little bit of a cameo, so we never went to the detail of adding all this extra stuff in, and it shows, you know, whenever you go to do this kind of thing. So let's have a quick look and we'll see what it actually looks like within the Excel spreadsheet. Okay, so I think what I'll do is I'll pause it just now and I'll go and bring it up. Okay, now I've gone ahead and added in the curve here in green, and this is the one where we have the systemic error, so that we're starting off at 0 and we're adding 0.1 and then adding 0.1 and adding 0.1, and we're doing that all the way up to 6.28, but each value of 0.1 is not absolute and correct. It's actually a little bit less than 0.1, so every time we add 0.1 on, we're adding that little error. So we've got that systemic error adding all the way through the entire curve here, and you can see that the final result is that the curve is slightly out. Okay, so that's just a nice little aside. I thought I would add it in just to show that I did actually work out that this systemic error would occur, but I thought, well, I was well just continuing with it just so we can have a look and see what the differences are, and now we can see right in front of us. So that's all for this video. We can go ahead and we can do the same for the cosine and the tangent, but I'm not going to go and do those. Tomorrow we'll go on and we'll look at something completely different. Okay, so thank you for listening. I'll get you on the next video. Goodbye.